This is just, I'll nip to the climate curves. And I don't want to go over these in great detail, but the PowerPoint is available, and it would be on hard drive around here if you want to dig into it. But suffice it to say, this is going from old on the left to young at the right. There's 400,000 years of information here. And the ice core data and the cave data and the seafloor sediment data, etc., show us these cyclical changes through time. This is 400,000 years. We've got a carbon dioxide curve on the bottom, and we've got a temperature curve on the top, and the carbon dioxide curve sort of wanders up and down like this, and it's now up here. The CO2 has risen dramatically, as most of you know, and that's an issue that we're all trying to get our heads around. The temperature curve, which is the upper curve, has gone up and down. And we've studied this enough, and one of the great discoveries that took place in my lifetime is we've recognized that cyclicity of the temperature curve is driven by orbital parameters. It has to do with the way the Earth goes around the sun, the tilt of the Earth on its axis, the wobble of the Earth, and the eccentricity of the Earth's orbit, each of which are parameters that change through time over varying time scales. And the cumulative effect of those orbital changes, subtle changes in the amount of solar energy arriving, particularly in the northern hemisphere of the Earth, is responsible for the coming and going of the glaciers, or the ice ages. And we understand that now. And that's the ice ages were driven by the sun. And the point that we need to make here, and if you take only one thing out of this room when you leave, the key thing to take out of this room is that we've now changed the system. We've jacked the CO2 up. Carbon dioxide in the Earth's atmosphere has risen to unusual levels. And we've reversed the experiment here a little bit. The Pleistocene, or the ice ages, were driven by changes in the amount of solar energy arriving to the northern hemisphere. We're now conducting a geophysical experiment on the Earth in which we've modified the character of the atmosphere, and we're now contemplating the impact of that modified atmosphere on temperature. And we're watching the increase in temperature associated with this change in the greenhouse gas content that you've all heard about. But we're conducting the experiment on this planet. And when I was a kid, we used to think we were going to go to Mars. We used to think we were going to travel. But it turns out that we're not likely to go to Mars. So we're doing the experiment on this planet, and it's the only one we've got. So we're experimenting, and we're in the test tube, and there's no control, and there isn't an alternative planet to go to if we don't like what we're doing. So again, as you contemplate, the future, you're going to be living in a changing test tube, and we don't have alternate test tubes to go into. So we've got 7 billion people living in the test tube with us, and we're all interconnected. So if I blow this up just quickly here, here's just a sketch of the last 40,000 years. You can see that we live in this interglacial time. It's a very nice time to live. Earth is relatively warm. It's climate is relatively stable, what we call the Holocene. But the CO2, which is down the bottom here, is climbing along here, and is now doing this. And there's our CO2. It belongs to us. We spawned it. We burn hydrocarbons. It's coming from burned hydrocarbons. It's modified the composition of the atmosphere. The modification of the composition of the atmosphere is leading to warming. And the warming is coming just, I think I've gotten until around 10:30. Am I not? Because I can see a clock. We've got about 10 more minutes. I'm going to tell you the warming. CO2 is the greenhouse gas that we're all interested in and concerned about. But the CO2 is a molecule that is rendered excited by the emitted energy of the Earth. The Earth absorbs the sun's energy, it emits it, and it emits it at a wavelength that excites the CO2 molecules in the atmosphere. There's not a lot of CO2 molecules in the atmosphere. If we took all the CO2 in this room and stuck it in, I could fit it into a large garbage bag. It's 380 to 390 parts per million in this room. If I did that, I'd fit it in a garbage. So there's not very much CO2. But the CO2 molecules, they vibrate faster as they get excited by the emitted radiation. They warm the air a little bit, and then the air accommodates the main greenhouse gas. And the main greenhouse gas is water vapor. The Earth's surface is covered with lots of water. There's 70+% surface water. As you warm up the air a little bit with the greenhouse gas of CO2, it accommodates more water vapor. As it accommodates more water vapor, that is a greenhouse gas. It gets a little bit warmer. As it gets warmer, it can accommodate more water vapor. And there's positive feedback effect there that you are going to watch happen. And I just want to nip back to this curve here. How many of you guys have seen this curve? Just a show of hands. So I'm always a little bit dismayed. And I'm sure that some of you are bashful and you've really seen it, studied it, and just not admitting it, but only about 10% of you raised your hands. This is a curve that we've named it after the guy who was measuring. This is the carbon dioxide content of the air. And it was initially measured in Hawaii by a guy named Keeling. We call it the Keeling curve. And it shows a change, a gradual increase in carbon dioxide content of the atmosphere. And it's a wonderful story. The guy thought that this might be happening. He was out in the Pacific. He measured up on the top of a volcano in Hawaii where you get the cleanest air possible that's coming across the Pacific. And then they wouldn't fund him. He was not funded. He was working for NOAA. They wouldn't fund him. But he gathered the data anyway. He was very interested in gathering this information. Despite the fact that he was not being funded, he still took his own time to gather these data sets, and he showed this gradual increase in the carbon dioxide content of the Earth's atmosphere. And you can see that it's got a sine curve superimposed on it. Why does it have a sinusoidal curve on top of the gradual rise? Why do you think that might happen? This is the northern hemisphere. If you go to the southern hemisphere, it's also got a sine curve, but it's out of phase. It's out of phase 180 degrees. Why would there be a winter and summer? Absolutely right. It's a winter-summer effect. There's a seasonal effect. In the summertime in the northern hemisphere, the vegetables are bringing in CO2 to build leaves and to build woody material. In the wintertime, that material is released. So there's a cyclical phenomenon associated. It's essentially the Earth breathing. So the biology of the Earth is breathing, but superimposed on this gradual rise. And it's our CO2. We've measured the isotopic composition of CO2. We've measured how much CO2 we're emitting from power plants. There is no doubt that it's our CO2. That comes from us. So man's CO2 is modifying the atmosphere, and it's changing the temperature. Let's see what's next here. Just to put it on one more chart, here's the flow for the last 400 years, and here I've got the temperature graph, I've got a CO2 graph. This is, again, a wonderful thing for me as a scientist to watch happen. We're taking the ice core data from ice cores, and we're matching it with the measured data from Hawaii. And the curves come together. The ice core data is in the black dots for CO2, and these little X's are the measurements. So you can see how the black dots merge right into the measurements. So two completely different sources of information, but they show the same thing. And then superimposed on there are little red things. That's us. And this phenomenon you're seeing here associated with the post-1800s, really the Industrial Revolution, it's been called the Great Acceleration. There's been huge changes since the Industrial Revolution on Earth, and it involves population growth. And the population growth is because of improved medical care, improved health care standards. So children live. Many children used to die. Now children mostly live. And populations have grown immensely. Our use of energy, our use of fuels has grown commensurately, also immensely. And this great acceleration is what you are living in. You are riding that rocket ship of change into the future, which is ill-defined. But who's going to define the future? Yeah. It's not going to be me, because I'm going to check out. And I'm leaving you guys with this situation. So what do we do? Let's look at it.